Good morning. This is Tim Stewart. I am president at Visual Decisions, and we're here today to talk about automatic data mining for process improvement. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve operations since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. So with that, let's go ahead and get started. We're going to take an initial look at the traditional methods for identifying and analyzing problems, and then we'll talk about how they can be automated using the Industry 4.0 toolset. So when we look at a typical improvement cycle, we see a six-step Kaizen process here. And step one and step two are to, first of all, identify the problems that we have out on the shop floor, and then to analyze the processes for the selected problem and figure out what are the root causes for our issues. And then we start the process of creating solutions to address those issues. Well, in terms of what problems we identify in the first place and how we prioritize those, what usually happens is one of two things. We very often end up just putting some grease on the squeaky wheel, or whatever the current most urgent issue is the one that grabs everybody's attention and gets improvement processes put in place for that. And so there's obviously a lot more that can be done in terms of identifying longer term trends, things that are just the way that things operate. There's a story here that I like to tell about a shampoo manufacturer that I worked with a few years ago, where they had an overhead conveyor that fed the filler of their operation. And in the data, I noticed that the filler was going down like every 20 minutes or so. So I went out to the line to see what was going on. And I noticed that very often the overhead feed would jam up, and eventually the filler would run dry because they couldn't fill any bottles anymore, and it would flash an and-on light. And the operator, wherever they were on the line, would have to see that and-on light flashing. Then they would make their way over to the filler, see that the overhead conveyor was jammed. They'd take a broomstick and they'd poke at it until the tipped over bottle cleared and things started filling again or flowing again. And when I talked to the operator about how often that happened and whether something should be done about it, he said, well, that's just the way it works. And very often those things are actually the biggest sources of loss for our operations, as opposed to catastrophic things like we see in the picture here that grab everybody's attention. And so when we look at which problems should get prioritized and how we identify those issues within our operations, it would be very good to have a more sophisticated approach to not only identifying the problems in the first place, but also measuring the impact of those and prioritizing them for implementing fixes. So then when we look at how we go about analyzing the root causes for those different things, there are a number of different manual methods that we can put in place, starting from the one that we were taught in grade school, which is who, what, when, where, why, how, and looking at if this performs differently when we have different operators or different times of the day, or different temperatures in the building, things like that. Looking at 5 whys and drilling down into more detail, doing the same thing with a fishbone diagram or Ishikawa diagram, but in a little bit more structured way. Doing graphical evaluation. My company is Visual Decisions, so we love graphical evaluation and being able to see those patterns in the data. Doing FMEAs or failure mode and effect analysis, and being able to really do a comprehensive look at the different types of failure modes that we have, and what are the different causes for those, all the way to more of a Six Sigma approach and doing statistical analysis of factors, whether that's an ANOVA process, analysis of variance, or design of experiments, a DOE, et cetera, and being able to utilize more of a data-based approach. But there's a lot of different ways that we can go about analyzing, those different root causes for failure. But this is typically a pretty manual process that we've done in the past. And depending on who's doing that evaluation, it can be, different levels of quality, different levels of depth of analysis, and you might get different results from, that process. So I talked a lot about, doing a lot of this kind of ad hoc and, a lot of the squeaky wheel or the latest problem and so forth. But a lot of companies are capturing data these days. And, whether it's an OEE system or an IoT or MES, and, capturing different events on the shop floor, whether those are quality based or downtime, and then, manually kind of going through the data to see, where the biggest losses are and, where we should be paying attention for these things. But it's still very often a manual process to, first of all, identify the failure mode in the first place and have the operator say, what actually happened. And then it's also generally a very manual process to actually go through the data and analyze where the problems are and what needs to be done to fix them. And so the next step in this process is really to utilize the machine learning capabilities to really augment the user knowledge. And so how can we apply that machine learning, the artificial intelligence capabilities to supplement what our people are already doing in the process? And so when we look at the role of artificial intelligence and machine learning, there's a lot of different capabilities there in terms of the data mining so that we can uncover, patterns and opportunities, classification systems that are going to help us ascribe different tendencies or different categories to different instances and so forth. So that's going to be when an event happens, what category should we put this event into and so forth. Neural networks and deep learning are going to help us really interpret that data that's coming from the systems and so forth, and also to make a lot of this more autonomous. So when I look at the different timeframes where we can apply these different things, there's really a couple of primary ways that we can do this. One is when we look at things that are in line, things that are happening right now. How do we automatically identify that we have a problem? And we can sense that pressures drop below a normal level, and the system can actually automatically identify what normal means, and then also identify the fact that we've dropped below that. And the system is able to do that, bring it to people's attention, even automatically create work orders and for maintenance, and get people's attention on that problem right away. And then kind of from an offline mode where we're looking more at historical analysis and a larger body of data, and really looking at what are the biggest problems that we have overall in our manufacturing process, and what are the different improvement events that we want to create that will help us optimize our manufacturing process as much as we possibly can. And so those are the two different kind of timeframes that we can look at, the real time as well as the historical analysis, the trends and so forth, that will help us really optimize things going forward. So then step one in this process, if we go back to that 6-step process for Kaizen, is to identify the different problems. And when we're looking at these different things, we're trying to automatically identify where performance, first of all, violates any SPC-like rules, to identify where we have quality problems, where we have performance issues, where things deviate from expectations. So we have an outlier that we're trying to identify, whether it's outside of established norms. And so I guess the difference between expectations versus established norms is an the expectation is where we're setting thresholds on where these things should be, and the established norms are more where things normally are, and the system can automatically identify what normal looks like. And then if we also see persistent patterns of behavior, those are things that are things that should be called out as well. And then when we're looking to prioritize those different potential issues that we find, we can look at the number of different events, the duration of those events for downtime, or the number of impacted pieces for quality, any associated safety issues, if we can tie things into that, costs. So if we are enriching our data to be able to say that downtime in this process costs us much more than downtime in this process, we can look at what the cost of those different downtimes is. And then if we see a potential for cascade, where if this fails, then these other problems are going to occur. I'll say a word about predictive analysis as well, where instead of looking at the problems that have already occurred, obviously with machine intelligence, we have the capability of identifying problems before they actually become problems, or before they become actual problems. So, first of all, we can look at trends within the data, and we're trying to predict an outcome based on different inputs. And so, from that, we can look at pressures, temperatures, vibration, sound, any number of different things. And from those input variables, or from those process variables, what we're trying to predict is an output. So is that machine going to stop? Are we going to see quality problems, et cetera? And there are a number of different things, whether it's neural nets or SVMs or random forests or any number of different tools that will help us both correlate those input variables to that output, as well as looking at how we can predict the probability of an event occurring based on what we see from those inputs. And so the predictive analysis is going to help us not only react to problems as they occur, but also to help prevent those problems from occurring in the first place. So step 2 in this process is analyzing the selected problem. So the question here is, can the analytics actually perform root cause analysis? In addition to just sensing the fact that, hey, we have a problem, temperature has dropped too low, the machine has stopped, et cetera, can they actually determine what the root cause of the problem is, in addition to just looking at, identifying the problem itself? And the answer is yes. And as I mentioned previously, there are classifier systems that allow you to kind of automatically group these different things together and help you identify these problems in different categories. But then we can also train the system to look at a number of different contextual clues to look at do we actually have information to automatically ascribe what the root cause of the problem is. And so systems can automatically do a lot of those analyses that we talked about earlier. So for instance, when we look at the 5 W's and an H, the system can automatically look at, is the performance the same between different shifts and operators and so forth, or if the problem is material dependent, does the material have the same problem on different machines? Is the problem dependent on the day of the week or time of day? How long has it existed? Is the magnitude of the problem changing, et cetera? But it can also be tied into very much like an FMEA process. And so when we perform an FMEA as humans, what we tend to do is start from that top level and work our way down. So we're looking at some particular function that is being performed. And so we may look at performing this particular operation. And then we list out what are the different potential failure modes for that operation. Then we get into the potential impacts of those failures and the different causes of why that failure would happen. And then we can start to look at, what are the different things that we can do to detect that particular cause of failure is actually occurring. What the machines are going to do is take the opposite view of that. They're actually going to start with that detailed information of temperatures and pressures and so forth, and work their way up that chain to get to, what is the failure mode that is occurring. And so as we structure all of this, it's actually very helpful to go through this type of an analysis, because as we can start to link the different failure modes with, how we would go about detecting those, we can train these systems to automatically observe when we see those individual conditions happening, that we see that cause of failure occurring, and then it can automatically classify what is happening within that process to those different causes. And so we can do that root cause analysis. Now, that is for things that we're able to train the model on. There's some capability, as I said, to do the analysis across different potential causal factors in an automated process, so that new or novel problems, we can identify things like, does it behave differently when different people are running that process? That can be done automatically for even a novel or new issue. But to do a true root cause analysis for something that is completely new, that's typically going to involve more of a human problem-solving process, in that new problem. So what are the lessons learned, and what are some of the key elements of putting these machine learning solutions in place? First of all, the machine learning capabilities themselves are obviously core. Having those neural net capabilities, having the possibilities of running the random forests or other mechanisms, so that you have kind of different mechanisms that will tie better or predict better for different situations. And so having many of those at your disposal is going to lead to better results. Obviously, it has to be tied into the data streams themselves. So having an IoT system or something like that that's going to be able to pull that data and present that to the learning algorithms and the processing is going to be very important. Having something that will help you create those algorithms and do the pattern discovery is very important. But then being able to visualize this data so that people can understand what the model is telling them is very important. But for me, the thing that's most important is to be able to tie this into your continuous improvement process, because simply raising your hand and saying that we have a problem doesn't help you at all until somebody actually takes action to fix and address those issues. Some considerations for selecting an enterprise AI solution. Obviously, the right data is going to be important. Connecting it to the right signal, and I'll talk about that in a couple minutes. Being easy to consume. Again, ultimately, your people have to take action on this information. So if the data is presented in such a way that only a data scientist is going to be able to understand it, that's really not going to help. You have to be able to have the output of this be something that your operators on the floor or your engineers can very easily see, understand what's happening, and then be taking action upon it. And this should also be connected and built into existing systems, so that people don't have to go to a separate interface to be able to see all of this. It's also extremely important to have automation in place. And so one of the things that I like to point out is that you want to be able to launch a project in a single click. And so if these systems are collecting information about what is the nature of the problem, what machine is it on, what time is it occurring, how often does it happen, or is it happening right now, some level of root cause analysis of what the underlying issue is, They should be able to see, a history of, if this problem has occurred in the past, what has been done to address this and so forth. And so you should be able to launch a corrective action in a single click, to be able to say, here's our list of problems. Here's ones that we know what to go do about it. So let's hit that button, get that assigned, or not even hit the button, but automatically create a work order within our maintenance system. Create Kaizen project for people to go and take a more in-depth view of how we go about resolving this problem. And then if you have done something like an FMEA in the process and you have suggested actions for different root causes, you can actually show those and actually recommend here's what you do when this occurs. And then as you're taking these steps to address these issues, capture those details of what is being done, update those FMEAs to say, did that recommended action actually address the issue and so forth, so that the next time something like that occurs, you can show those same recommendations and show what has been the result of these fixes in the past. So I talked a little bit about what data should be gathered and really how to know in advance. And the first question that we have to ask is, where should we be gathering data? It's a big shop floor. So do we gather data, everywhere, or do we start, in certain places? And the most logical places are, first of all, if you have critical processes, start there. It's easy. But also, if you have a process that's out of control currently, then go ahead and start gathering information from that one as well, so that you can start to improve that process. Once you've identified where, you can start to utilize one of those above frameworks to kind of hypothesize about different potential causal factors. So if you've done a FMEA on that process and you go through and you start to identify what are the different signals that we can monitor that will tell us when this causal factor is going to occur, you can put those plans in place to collect and analyze that particular data, so that now you have that available that you can tie back into that classifier system and automatically say that this signal tells us that this problem is occurring. And then put control plans in place to monitor those factors and take action when you see something happening. It's also important to cleanse that data and really be confident that the data that you're seeing is real data that is reflective of what's actually happening in the process. So make sure that you're analyzing the data for any type of anomalous results. Sensors will get dirty, faulty, etc., and you have to make sure that the data that you're seeing looks normal. And so you can actually set up a machine learning system to identify when the data itself looks anomalous and report that, in addition to analyzing the data as if it's good. And so it's basically just a separate process that you set up to predict when the data itself is a problem, as opposed to when the machine that the data is representing is a problem. If the sensors aren't reporting any data, it could be broken sensors, network issues, etc., just missing data, that should be another alert. And then if you have humans inputting information into this as well, so very often, human input will be a part of this process. And so when the machine goes down and you're looking at that downtime and you're trying to train the system to predict different types of downtime, you may have people putting in what actually happened. And so that output variable that you're trying to predict of different failure modes may be trained based on that human input. And you have to make sure that that isn't lazy input where they're just picking the first thing, the first button that appears on the screen. There's no unit of measure errors or anything like that. And just have good screening process in place to make sure that the data that's being put in by people that your system is relying on is going to be quality data as well. and other things as well. But just having those data cleansing processes in place are very important to the long-term success and validity of what you're predicting here. So that's actually it for today's video. We have a number of upcoming webinars that are going to discuss other issues as well. So next week, we'll be talking about improving setup times with Industry 4.0. And then in the future, reducing cache-to-cache cycle time, visual factory, 8D problem solving, etc. The one on the 23rd of February is actually one that I'm pretty excited about, fighting performance entropy. And what I actually mean by that is that I had a great quote from the person that ran continuous improvement for all of UTC, United Technologies. And he said that if we had been able to retain all of the gains that we've had from our continuous improvement events over the years, we could just drive the truck past the factory and the materials would spontaneously form themselves into the end unit and fly themselves into the truck as it was driving past. But what happened in actuality was that they would have a Kaizen team go out, look at a process, they would make an improvement, they would see a significant improvement in results, and they'd come back after 6 months after that project team left, and well, performance would be back to where it was initially. And so you have this entropy that you're fighting against from a continuous improvement perspective. And what we're looking at in this presentation will be how we actually address that, so that when you make those performance gains, you can retain them over time without having the team standing at the process keeping watch. So with that, I thank you. If you have any questions, please reach out to me at tim@visualdecisions.com, or you see my phone number there. And I look forward to hearing from you in the future. Thank you. Bye-bye.